Hello and welcome to a video lecture for CVEN 2320 Differential Equations for Civil Engineers. I am Venki Urameri, and in this video, we'll be talking about solving second-order non-homogeneous ordinary differential equations using the method of variation of parameters. As an outline, we will first talk about what the method of variation of parameters is, and we will see how we can use it to solve second-order non-homogeneous ODE. We'll also look at some of the challenges that are associated with this method and some ways to overcome them. And finally, I'm going to present a few illustrative examples to show you how we can apply the variations of parameters approach. Method of variation of parameters is another method to solve ODEs. In particular, it can be used to solve linear non-homogeneous ODEs of any order, including first order, second order, as well as higher order. We don't use this method with first order ODEs because we have better methods such as the integrating factors approach that does a better job at solving first order ODEs. But these certainly come in handy when we want to solve second order, higher order ordinary differential equations. Our solution in this approach consists of two parts. The y sub c, which is the complementary function or the solution of the homogeneous component of the ordinary differential equation. And then we have y sub p, which is the particular solution, which is the solution for the non-homogeneous or the heterogeneous. So one of the big advantages of this method is that our forcing function f of t, which appears on the right-hand side of our differential equation, need not be of a specific type. If it's either a polynomial, sine, cosine, or exponential function, or finite combinations of these functions, then we could use the method of undetermined coefficients. But the good news here is that f of t can involve any functions or any of the mathematical expressions. So this approach is much more generic than the method of undetermined coefficient. So the forcing function is f sub t. This can be any type of continuous function. And then one of the advantages of this approach is that the method of variation of parameters guarantees a solution up to an integral. And what I mean by that will become clear to you, in a few short steps. But one thing is we can come up with some sort of a solution, at least up to an integral. The challenge is, however, the integral may not be easy to solve, so we'll have to resort to some other methods to solve it. So the algorithm behind solving this variation of parameters or applying variation of parameters to the second order ODEs is first, we solve the homogeneous part. In the homogeneous part, essentially, we take our differential equation and equate it to zero and then solve it. If you have constant coefficients, then you can solve them using the characteristic equation, the quadratic equation, and guessing bases and using those bases to write your original. The second part of this approach is to identify what is known as the Wronxian. Wronxians are essentially a determinant that consists of constant terms and are functions of x. They essentially take the basis y1, y2, which are the solutions of the the second order homogeneous ODE, and then they take its derivatives and then use that to create a Wronxian. And then what we do is once we have the Wronxian and we have the homogeneous part, the basis of the homogeneous part of our equation, we are going to assume the basis for our particular solution to be u and v. And we make use of two equations to solve for them. So one is that u prime y1 plus v prime y2 is equal to 0. And then u prime y1 prime plus v prime y2 prime is equal to f of x. Again, prime means we are taking the first derivative. So in the first case, we have u prime and then y1. Y1 is known to us, v prime, which is unknown, and y2, which is known to us because that's the second basis for our homogeneous part of that equation. We equate it to 0, and then we say that u prime, y1 prime, again, we know y1 prime because if we know y1, we can take its derivative and get prime, and then v prime is unknown, and then we can similarly take the basis y2, take its first derivative, y2 prime, which is equal. So using these two equations, two unknowns, we can solve for u prime and v prime. And once we get our u prime and v prime, we can integrate them to get our u and v. And then once we get our u and v, we write the particular solution y sub p is equal to u of y1 plus v y2. And then the complete general solution is the sum of the complementary function, which is the homogeneous part, plus the particular solution, which corresponds to a forcing function that's on the right-hand side. So you get that equal to a y1 plus b y2, u y1 plus v y2. This, again, is A and B come from your initial conditions. U and V directly come from our solutions of the particular solution. So we can also come up with a formula for obtaining the particular solution, and that a formula entails integration, and we can write it as y sub p equal to minus y1 integral of y2 times f of t dt divided by the Wronxian of y1 and y2. The Wronxian, again, is the determinant, which is y1, y1 prime, y2, y2 prime. And essentially, the value of this Wronxian is a cross multiplication of y1, y2 prime minus the y1 prime, y2. So we take the diagonal element and subtract the off diagonal element, and that's how we get the value of the Wronxian. Because y1, y2, y1 prime, and y2 prime are functions of x, the Wronxian will be in terms of t or x, whatever your independent variable. Similarly, your y2 and y1 that's within the integral is also a function of t. So we can see that we can write the particular solution up to an integral because we know this is the formula, but solution of these integrals sometimes can be a challenge because they may entail complex or fairly complicated functions that we have to integrate. So if we look at the variation of parameters, um, it is easy to get the solution up to the integral form because we can calculate y1 and y2, which are the solutions to the homogeneous equations. And we know how to do that fairly easily, especially constant coefficients. And then we can also calculate the Wronxian because it is just a two-dimensional determinant, which is easy to solve. But these integrals are what becomes problematic. So when we want to, we can get this particular solution up to an integral, which means we can write in or fill in all the terms for this integral, but we may not be able to analytically solve them. If we cannot solve an integral analytically, we can, however, solve these integrals approximately using numerical method. So I'm going to talk about one numerical method or a couple of numerical methods that we can use for these purposes. And then to solve integrals numerically, we have to solve them as definite integrals. So we have the lower bound T naught, which is typically equal to 0, but it can be any T naught, which is initial condition, and up to T where you want this. So you have to integrate from T naught to T, and then the same thing, you have to integrate this function T naught to T, and then you can get the values, plug in T for Y1 and Y2, and you will be able to get your YPT that way. So keep in mind that if we want to solve the integral arising for that particular solution numerically, we have to convert it from an indefinite. So how do we solve definite integrals numerically? There are several methods that are used to solve them. Here I'm going to list a few. The general quadrature is also known as the adaptive quadrature, and this approach is one of the widely used methods for solving definite integrals when your function is known, the integration function is known. You can also use Gaussian quadrature, which is a slightly simpler approach than the general quadrature to solve for, to perform numerical integration. There are other techniques such as the Romberg integration, which is also uses a series solution to solve your definite integral. So essentially what these methods do is they take your function and then they recognize that the solution to the definite integral is nothing but the area under the curve, and then they find ways to approximately calculate the area under your curve using quadrature or Romberg integration. Alternatively, you can take or assume a set of values of x or t, and then calculate the corresponding values of y. And then you can integrate the data that are presented in samples using what is known as trapezoidal rule or Simpson's rule. Trapezoidal rule essentially plots a curve and then assumes that the curve is made up of many trapezoids and then sums up the areas of the trapezoid to give you the value of that. So these methods are been around for a long time. They work well, at least in an approximate sense. They give you a reasonably good solution. And also, they are implemented in Python, so you don't have to do much work to solve these definitive. So scipy.integration, the integration module in scipy, has functions actually for all these methods, and you can use one. So, having known what the solutions of the particular solution of the differential equation looks like, what we will do is we will jump into a few illustrative examples to see how we can solve our second order ordinary differential equations using variation parameters. In the first example, I'll make use of the algorithm to solve it, which is writing down the two equations where our u prime and v prime are not known, and then trying to integrate. So let's look at an example. Y prime plus y is equal to secant of x. This is our second order ODE that we want to solve. And keep in mind that we can only solve this using undetermined coefficients if this was not secant, but either a sine or cosine. Because it's secant, we cannot really use the method of undetermined coefficients. So what we'll first do is we will solve the homogeneous equation, which is we'll set this right-hand term to 0 and solve for y double prime plus y is equal to 0, and the solution for the characteristic equation, this time it has complex roots, and the real part is 0 plus or minus 1 times the imaginary part. So because of that, our basis y1 is equal to sine of x, y2 cosine of. So once we have our y1 and y2, our yp is u times y1 plus v2. And we also have two relationships from our algorithm, that is u prime y plus y2 is 0, and then u prime y1 plus v prime secant. So I can plug in for y1 and y2, which are sine x and cosine x, into my first equation. I get u prime sine plus v prime cosine x is equal to 0. And then I take the derivatives of y1 prime sine x cosine x, y2 prime cosine x sine x. So I can plug that in into this equation here and write u prime cosine x prime sine x. And then what I can do is multiply the first equation by sine x and the second equation by cosine x to eliminate this v prime. So this will be sine x cosine x, this sine x cosine x. Of course, these two terms will be square x and x. And if I sum it, I get u prime sine square x plus square x is equal to 1. Of course, you know, which implies u prime is equal to 1, and u is equal. So basically what we've done is, again, secant x times cosine x will become equal to 1 because secant x is nothing but the cosine x. So I got this 1. U prime sine square x plus cosine square x is 1, or u prime is 1. And if I integrate, and when I know u is equal to x, I can plug this into the first equation and calculate my v prime, which is equal to cosine square x minus 1, which is equal to minus of 1 cosine square x, which is equal to minus tan x, or v is equal to natural log of. So I'll be able to solve these two systems of equations and get my u prime, v prime, and from there I can integrate and get v. And then once I have u v, I'll be able to essentially write my complete solution as being equal to the complementary function plus the particular solution. Complementary function is the function, the homogeneous equation part of the equation, which is a sine x plus cos x. And then particular solution is uy1 plus 2, and yp is equal to x sine x cos x times cos x. And if I uh, sum them all up and pick the sine x and the cosine x terms, I get y x sine x and b plus natural log of cosine x times cosine of. So a and b can be obtained if you know the initial conditions. And again, remember, particular solution has no unknown coefficients because it is solving for that forcing function that appears on the right-hand side. You can quickly check this by plugging in that equation into SymPy. Use Python and use the symbolic math library SymPy, and it gives you the same results. Instead of a and b, it is giving us c, but those are constants. So uh, this serves as a check to show us that the equation that we got by applying the algorithm works. Let's go on look at another example. And in this example, I'm going to again solve a second order differential equation with a forcing function. This time I have an exponential forcing function that's in the denominator. So as usual, I solve the homogeneous part by setting the differential equation 0, and I get lambda squared minus 3 lambda plus 2 is equal to 0. And when I solve for it, the roots are lambda 1, 2, and that gives me the basis of e to the power of minus 2. And this time I'm going to get the Wronxian determinant, which is y prime y2 e to the power of minus t and e to the power of minus t. And then their derivatives in the second row, which will be minus e to the power of minus t, is the derivative of this element. And then if I take the derivative of y2, it'll be minus 2 to the power of minus. And essentially, the value of this determinant is obtained via cross multiplication and subtraction. So e to the power of minus 2t times e to the power of t. And then the negative of the negative becomes positive. So I get e to the power of minus t times e to the power of minus t. And if I perform some algebra on this e to the power of minus t, power of minus 2t becomes e to the power of minus 3t. And then I have minus 2 here and 1 here because power of minus 3t. So I can factor out that e to the power of minus t and write minus 2, 1, which is power of minus. So that's your Wronxian, the value of that Wronxian. And now I can plug all these values. I know my y1, I know 2, I know my f of t, I know my w, the same thing for this. So I can go back and plug all of these values and substitute and simplify, and I'll end up getting an equation. And this equation is essentially telling me the value of that particular integral up to the value of the particular solution up to the integral format. So as I said, this method always brings you, it's easy to get to this integral. Whether you're able to solve this integral or not is a different story. Okay, so in this case, we're just going to leave it here at this with this integral. And then what I'm going to do in the next example is show you how we can numerically solve this equation for those integrals. So what I want to do in the third example is I want to solve the integrals of the particular solution. And I have reproduced that equation here along with the values of y1, w, t. And I want to do this over and make a plot over a range of t being equal to 0 through 10. So I want to see how my solution varies between 0 and 10. So I want to make a plot. So to do this, what I have to do is essentially, I want to integrate from 0 to some value between 0 to 10, and then do the same integration, calculate the value, and keep repeating it for various levels of t going from 0 to 10. So I have to do this, not only do I have to integrate it, I have to integrate it several times to create a set of points which I can then plot. Okay, so this is best done using a for loop of some sort or some looping using Python. So there are many methods that are used for doing this numerical integration. So we'll make use of one called quadrature. Quadrature essentially takes this definite integral a to b f of x dx and converts it into an algebraic expression that I can sum over n points. Okay? So that is the idea behind Gaussian quadrature. And then essentially it says that this integral is nothing but the weighted values of function of x at various levels of n. And then these wi and xi are known to you a priori. They're tabulated, they're built into Python, so you really need not go into it into much detail. And when you call the function, it goes through this function, solves the corresponding values and value. So how do we implement? Well, the scipy.integrate library has the functions. So the workflow is first we import that scipy.integrate. Then we create functions to integrate. We set the upper and lower limits. We call the integration functions, and then we perform other calculations that are needed to calculate y. Again, as we want to plot over several values, we need to put the last two steps, which is calling that integration function and performing other calculations into a workflow, into a loop, so that we can do that every single. So here's our Python code. So our step one is to import the libraries. So from scipy.integrate, from scipy, I'm going to import integrate, and the integrate gives me the quadrature formula, and then I'm going to import numpy as np. It helps us with calculations. Then I have written my first integral. So I've written a function for the first integral, and recall that a function is always defined using the def keyword. And my function is called I1x of t. So it takes t value and then goes into the function, calculates y2, calculates w, calculates f, and then performs what the integrand is, which is y2 times f w, and returns that as a value of. Similarly, the I2x is the second integral that I need in my particular solution. Here I calculate y1, I calculate w. Again, I pass in t, and for that t, I calculate y1, I calculate w, I calculate f, and then I calculate I, which is equal to y1 times f w, and then I return that I. So once I return these two, these are the two functions, and now I want to call these functions over a range of values. So the range of values are, I'm going to start at 0.01 and go up to 10.1, and then in increments of 0. So it is showing me I'm going a little over my 0 to 10 range, but essentially I could have just gone till 10.01 to cut off it. My lower bound of integration always is 0. And then I'm creating an empty array or an empty list, yx, to store my values. And then here, what I'm doing is I'm going to loop through, and I say for I in tx, remember, has got all these values. So as I loop through, it will take each of the value and use that to calculate my y1, y2. Again, I use that to calculate my I of x going from 0 to I. So this is the definite integral that it does. And I'm using 75 points for my Gaussian quadrature. And then what it does when you imply Gaussian quadrature is it gives you the value of the integral, and it also gives you the error of the integral. So we are parsing out the value and the error. We are essentially discarding that error because we don't need it. So we are only going to keep I1 value, and I2 value is again the value of this integral that we need as part of our y sub p. And then I'm going to calculate my y sub p, which is minus y1 times I1 plus y2 I2, which is the particular solution. And once I get the particular solution for a given value of x, I'm going to append that into my list x so that I have values of the particular at many different points in the range of 0. Again, remember, I can't start at 0 because integral between 0 and 0 will not yield anything meaningful. Your lower limit, your upper limit have to be different, and your lower limit has to be lower than your upper limit. So I'm going to start somewhere very, very close to 0 and then keep moving. So the final step is I'm going to import matplotlib. From matplotlib, I'm importing pyplot as plt. I'm going to make a plot between tx and yx using r dash. So I'm going to get a red line. I've labeled this numerical. I'm going to plot my x label as x, y label as, r y sub p, which is basically y sub p, which is your solution. And then I'm going to plot my legend, my title, my grid, and show it. So when I run this code, I'm going to get a value that looks like this. Here's my title, particular solution P. Y sub P is what I'm plotting on the y-axis, and then X is what I'm plotting on my x-axis. And you can see that it starts off at 0 and goes up and asymptotically approaches 5. This is because e to the power of minus t assumes a value of 1 for very large t values. As t becomes higher, e to the power of minus t 1. So 1 over 1 plus 1 is 2. So this is where it kind of ends the value. So this is where it is asymptotically that value over time. And again, as I said, this is, even though the curve is very smooth, note that numerical integration is approximate. And also because we are dealing with exponential functions, the lower end values may not be as accurate as higher end values because, as you know, exponential values at small arguments or at small values of x tend to be fairly small. So the round off errors can have a much significant impact than, say, when the numbers become large, the round off errors have a smaller impact. So that is the gist or the idea behind numerically solving that integral and getting the particular. So as engineers, we're always looking for ways to solve mathematical equations in as convenient a way as possible. So the method of variation parameters, we can perform the math, come to at least an integral, and if that integral is not something that is easy to solve, then we can approximately solve it using the numerical methods, quadrature, Gaussian quadrature, and come up with. So, what you should know at the end of this lecture is how to solve linear non-homogeneous second order ODEs using the variation of parameters. You should know that this is a general method that is applicable to all forcing functions. Your right-hand side, the function on the right-hand side of your non-homogeneous equation need not be of specified types. It can be any continuous function. It also involves integrations, which may not be easy to do. And of course, you can explore the idea of numerical integration to solve that particular solution numerically. And of course, Python can help because there are some built-in libraries, particularly with SciPy, that can help you do this. So with a little bit of Python, with a little bit of mathematics, you'll be able to solve a wide range of second order non-homogeneous ordinary differential equation method of variation parameters. I hope you found this video useful, and till the next video, take care, stay safe, goodbye.